Greetings, dear colleagues. My name is Viktor Stovba. I'm PhD at Applied Mathematics and a research officer at the Glushkov Institute of Cybernetics. Today we talk about subgradient method with Polyak step in transformed space of variables. And let us start. So we're going to discuss the following problem. Find x star. This is the argmin of the function f at x with known f star. F here is a convex function with known optimal value. Actually, there are a lot of situations where when we know this optimal value, but even if we don't, we can use some estimates, lower or upper, of this F star and use the algorithm that we are going to discuss. So here F is convex, it's very important. And now we do not concentrate on smoothness of this function. So the first thing that comes to our mind when we think about solving this problem is the gradient descent group of methods and its well-known form, the steepest descent method, which is on the formula 2. Here we have a monotonous sequence of values of the function f at the minimization sequence that this method builds, and it converges under some assumptions. And these are f must be convex, gradient of this function f at point x k must be Lipschitz, and we need to choose some alpha k steps of this method for it to converge. If our function f is non-smooth, we can use subgradient method, which is the formula 3. This is the analog of the usual gradient method, but here instead of gradient, we use a subgradient of the function f at point x k. And here is any subgradient. We can choose step alpha k, which is greater than 0 in different forms. And for each of these variants, we have some theorem that shows us that this method converges. But nevertheless, subgradient method is not a descent method. It means that we cannot guarantee that value of our function will be decreasing at each step, so that we fix function records. This is the value that you see on the bottom of the slide. So we have two methods, but for some functions, they can work pretty bad. For example, the Rosenbrock function. Actually, we can use gradient descent and subgradient method for this to minimize this function. And at this picture, you can see the trajectory of the gradient descent. As you see, it goes pretty fast here, but it starts some zigzag trajectory. And when it goes here to the area where the minimum point lays, it starts to zigzag rather often, and the number of iterations radically increase. So for such kind of functions, which are a lot of, I mean, raving functions, we need to have some efficient method to find their minimum. So what are the good method requirements that we seek? It must minimize both smooth and non-smooth functions. Also, it must minimize raving functions, like I presented at the previous slide. Also, ideally, like we need to know that this method converges and when it converges, and also how fast. Moreover, it would be really good if we could minimize the function of a large number of variables. Yeah, I say like about 1,000, 10,000, 100,000, or even millions, since we usually use this for machine learning problems where we have a lot of input data. Also, it would be great too to simplify some implementations of this algorithm. It should be easy to implement in different programming languages. We need to have some space for modifications of this method and so on. But these are the main. So let us now talk about subgradient method with Polyak step, which we are going to call method A to simplify. So the origins of this method, you can see on the slide. It goes deep to works of Eggman, Motzkin, Schoenberg in 1954, Yeryomin in 1965, and Polyak in 1969. If we try to go deeper, we can find some roots of this step in works of Altman, Albert, and a lot of other scientists. So the subgradient method with Polyak step, or method A, has the following form. It's the formula 4. We need to recalculate the next point using our previous point and two multipliers. The first one is hk, which is the Polyak step, actually. And the second multiplier is normalized subgradient of the function f at point xk. So hk is the Polyak step, or also we can see it as AMS step, which goes to first letters of surnames of Agman, Motzkin, and Schoenberg that used this method. Moreover, in this step, we have some scalar multiplier parameter m, which is greater or equal to 1. And this is the convexity shift. Actually, it allows us to accelerate this method for some specific kinds of the functions. So what do I mean? We have the inequality 5, and we consider functions, arbitrary convex functions, for which this inequality holds, where gfx is subgradient. So this scalar parameter m is a maximal convexity shift of the function f. So what does it allow us to do? It allows us does not cut localization of the optimal point x star, and allows us to consider some special types of functions. For example, if we have arbitrary convex piecewise linear non-smooth functions, for them we have m equals 1. If we consider quadratic smooth functions, we can use m equals 2, and thus accelerate our step and speed in 2 times. Moreover, we can consider homogeneous differentiable with parameter sigma functions. For them, we have m equals sigma. So if it's 5, we can use m as 5 and accelerate it in 5 times in terms of step. So for this method, which is actually the usual subgradient method, but with specific step, which is called Polyak step or AMS step, we have convergence statement and theorem. So statement 1 on monotonous distance decrease says actually that the sequence generated by this method satisfies inequalities, which mean that the distance to the minimum point decreases as iterations go further. This is like a part of the theorem on convergence, and it says that if f is a convex function, then in this method, xk leads to x star, sk leads to infinity. So this is the convergence theorem. Moreover, for this method, we have some theorem 2 and 3 that proclaims the convergence rate for arbitrary convex functions and for convex functions with acute minimum. So the first theorem, theorem 2, says that for the sequence generated by the method, the following inequality is true. Its lower limit of this value equals 0. Actually, it means that we have this inequality is true, but since subgradient method is not a monotonous method, so we use here records. So this method converges, and convergence in it works for records. So this inequality holds for records, which are defined like this. Also, we have theorem 3, and if we consider convex functions with acute minimum, for which this inequality holds, then the method 4 converges with rate of geometric progression with a common ratio Q1, which is here, and C1 is some constant that bounds norm of the subgradient GFX. So the geometric meaning of the method A says that we have some function f, and it is approximated by the function of this kind. And the step hk is chosen so that this equality holds and the condition 5 holds that I proclaimed before. To see how this works geometrically, let's look at this slide. And if we start here from the point x0, we have this point then, and we move as far as the f star value sets, which is here. So until we intersect with this line. Here we have x1. Then we use value f at x1 and do the same thing. So move to the line to the point where f star sets. And here we have x2. And so that we continue. So let's look at some computational experiments with this method. And first is the piecewise linear function, which is the sum of two absolute values. And this function is stretched in one way, which is x-axis. For it, we can use this method. And if we set m equals to 1 and start with the point 1, 1, which is here, we obtain this zigzag trajectory of the method, which is shown on this picture. At this slide, we can see some numerical results for piecewise linear and quadratic functions. And for the first function, we can use only m equals 1. And for quadratic function, we can use m equals 1 and also 2. Number of iterations for m equals to 1 are presented in parentheses here. So in this table, you can see a number of iterations for different accuracies. And as you see with red color, we highlighted number of iterations for this method if we used m equals 2. So here in comparison 36 with 1947, it's quite big decrease in iterations if we have t equals to 10,000. So this function is strictly raving, and it's stretched. Its contour lines are stretched in x2 axis pretty strong. Here we take a look at the quadratic function, and matrix D here is a diagonal matrix, and diagonal elements of it are generated within this formula. We have some alpha values, and changing these values, we can affect eigenvalues of the matrix D. The optimal value here is all ones, and f star here is 0. Since it's quadratic function, we can use m equals to 1 and 2. As a number of variables n, we chose 10 million, and the accuracy 10 power to minus 20. As you see, iterations highlighted bold, we have pretty small number, like 45, for all m equals 1 situations with all ratio of eigenvalues, max and min. And if we have m equals to 2, we have 42, 27, and it decreases as the ratio decreases here. Now let's move to subgradient method with Polyak step in transformed space, which we are going to call method B. And it moves us to some space transformations. Origins of this go deep to Shor's ideas, and more precisely to second idea, which is to use linear non-orthogonal space transformations for improving properties of a function to be minimized in transformed space of variables. And method acceleration means that we transform our space of variables so that some properties of our functions be better in transformed space than in the initial space. Here we talk about contour lines and how strong they are stretched. So the less they are stretched, the better subgradient method with Polyak step works. Examples of these methods are ellipsoid method, R algorithms, and a lot more. So to make this transformation, we need to change the variables by this formula. Here B is a non-degenerate n times n matrix. So we create new function phi at y, which equals f at by, and its subgradient. These subgradients are connected within this formula. And moreover, the optimal values phi star and f star are connected as well. Also, we have some analog of the inequality phi, which must hold 2. We consider functions for which this inequality holds. And the subgradient method with Polyak step in transformed space, you can see here is a formula sticks. And if we want to rewrite it in transformed space, so within variables y, we can do this, and it's a formula 7. And as you see, it coincides absolutely with the method in the initial space without space transformation. It means, and it shows us that this is like not two different methods. This is one same method, but it works in transformed space of variables. This transformation is defined by this matrix B, which sets here and in other places. Moreover, we have some remark which says that if B, this matrix B, equals to identity matrix, then the method B coincides with the method A absolutely. Since method B is the same as method A with space transformation, we have also statement 2 and theorem 4 on convergence for convex function. Also, we have convergence rate of the method B. These are method 5, theorem 5 for arbitrary convex functions, and theorem 6 for convex functions with acute minimum. So the same statements hold also for the function, new function phi, for sequence y, k, generated by the new method in transformed space, and also for convex functions with acute minimum. We have this geometric progression convergence with a common ratio Q2 here, where C2 is a constant which bounds norm of subgradient G phi at point Y. So here you can see the iterative process for both methods. And the only difference here is that in the method with transformed space, we use n times n matrix B. And all other things that we start with are f star, parameter m, x0, and epsilon, which is greater than 0, which is needed for accuracy. So at first step, like if we set now that we are at kth iteration, we have the point xk, and to move to the second iteration, we need to perform some steps. These are 3 steps. The first one is to calculate value of the function f and its subgradient at point xk. If this inequality holds, we stop and fix iteration and optimal point. If it does not, we calculate the next point within these formulas and move to the next iteration. Now take a look at results of computational experiments with the same functions. Here we have piecewise linear function, but for the method with transformed space. Space transformation here is defined by this matrix B. And as you see, the trajectory of this method, it converts faster, much faster than the method A for the same function, considering that this contour line of the function x1 plus 5 apps at x2 are stretched as well. Here we consider piecewise quadratic function, which is strongly Raven function, so-called, and here we use the same matrix of space transformation. And on the next slide, we are going to see 2 trajectories. The blue trajectory responds to method A with m equals 1, and red trajectory corresponds to method B with the same value of m. So here you see that when our red trajectory of method B shows us that in 4 iterations we get to the minimum point with required accuracy. At 4th iteration, method A stops only here, which is pretty far from the optimal point that we want to reach. The last table shows us results for quadratic function. And here we consider both methods A and B with both variants of value m. So the first part of table is for m equals 1, second part is for m equals 2. So like the second column here is the worst number of iterations, which is like the hardest situation when we have m equals 1 and method A. And the last column is the best, actually, because we use method B and m equals to 2. So here you can compare 12 with m equals to 2 and method B compared to 70, which is for the same function when we have method A with m equals to 2. So comparing with this number, for example, we have 341 and 2 iterations, or for 10K, we have 3,635 compared with 12. So the increase in number of iterations is pretty big. So the last thing that we consider is any problems and solutions of these problems that subgradient method with Polyak step has. So the first one is parameter m selection. So how do we choose this parameter? Actually, m equals 1 always fits. And if our function lies in area of these special types of functions, like quadratic or homogeneous, differentiable, we can increase this m. And usually in practice, we can increase this m manually and see if our method converges. If it does, it means that this function lies in area of these functions, and this m can be increased more. So it's like empirical way. Moreover, we can use this analytically and just check that inequality 5 if it holds, but sometimes it's not always easy to do. And also we could have some information about type of a function to be minimized. Then we could say which parameter m we could use for it. The second problem is matrix B selection, and it depends on a function to be minimized strongly. So for every other function, there could be other matrix B selection. So what does matrix B mean? It means that we transform our space in direction of axis and their convex combination. If we transform it in axis, it means that we use and set diagonal elements of matrix B. If we use non-diagonal elements, it means that we transform space in convex combination of axes. So using this and know some information about function, we can set how and in which direction we want our space to be transformed. So it all goes about empirical way of choosing this matrix B selection. Unfortunately, there are no any analytical ways of choosing this matrix B, and it's still under investigation area. And the main advantage of this method, this gradient method with Polyak step, it's its simplicity. We saw the iteration process. It's pretty easy to implement at any programming language. It could be Python, it could be Julia, or any other. And moreover, the minimization of functions of a large number of variables, it is real for this method. We saw quadratic function with 10 million numbers, and it converges in like 45 iterations, and it took it could take like seconds to perform. So the original subgradient method with Polyak step, or like Pollak's method, it converges really, really fast for functions of a large number of variables if the contour line of this function are not stretched in any direction. So if they are really close to a circle, we could get our minimum point really fast. But if our function is Raven, here is the point where the problems starts. So in this case, we just need to transform our space so that these contour lines become better, and then our Polak method just does its work. So here are some references that you could seek, and these are Shores, Agman, Moskin, Yerevin, Polyak, and Sergienko and Stetyuk works. Also, we have acknowledgements since this work is supported by Volkswagen Foundation grant number 97775. And this is the end of my report. Thank you for your attention.